All right, good morning, everyone. First thing I want to announce is that I will hold class as usual next week. I plan to be here. I usually arrive on campus around 8:15. That's when my bus gets here. Next week, I have no idea if the buses will make it to campus or not, but I plan to be here. So even if the bus drops me outside of campus at 8:15, that gives me about 45 minutes to hike in. So hopefully I'll be here by 9 o'clock. If your class is at 10 o'clock, so it shouldn't matter. If you're in the lab, again, it shouldn't matter. If I'm on campus, that's my plan. I want to hold class as usual. That's one thing. Second is we will have quiz as usual on Monday, always at the beginning of class. And I think I sent an email about this, but I'll repeat it again. So every Monday class at the beginning, we'll have a quiz, and the quiz material, the topic under assessment, will always be the topic we learned in class the preceding week. So the stuff that we learned this week, Monday, Wednesday, Friday, will be tested on next Monday. That's always the planned schedule. Homework, again, is the same thing. Right now, all the homework assignments on mastering are set in June, which is like the end of the academic year. Just because if I don't have a due date for all the assignments, the system doesn't let me assign it to the students. So students would not be able to see those. So I put in like a due date of June for now. But as and when we complete a topic in class, I will, consider the topic assigned, and I will change the due date. So keep looking at your Canvas calendars. Okay. Every assignment will show up on your Canvas calendars. So I integrated, there's an integration tool, and I integrated those assignments in Canvas. That's the purpose. So students need to keep checking their calendars. Let's see. All right, having said that, let's continue with our topic. Yes. Yes. Yes, that's always an option. So the question being asked is, can we attend class over Zoom and take the quiz over Zoom? And that is an option available to all students. Some of my colleagues have informed me that some students in their classes made plans to like go home for the week. So if you have made plans to do that, it's absolutely fine. You can do that. You can always attend class over Zoom and take the quiz over Zoom. Okay, you don't need any special permission. You do not need to notify me if you want to do that on Zoom. That's an option that's available to all students from the beginning. Okay, any other questions before we jump in? All right, let's get to our topic. And let's see. So we were discussing the series parallel equivalent analysis technique, right? We take a large network of resistors, we reduce it down to one single resistance, we apply Ohm's law, and we calculate the voltage and the current as the case may be. In this specific example, we had a voltage source and a bunch of resistors. So we reduce all of those resistors down to one single resistance. Now we have V from the voltage source, and we have R. We apply Ohm's law and we calculate I. If it was a current source, as we will see in the next slide, we have a current source. We would have I and we would have R. We apply Ohm's law and we calculate the voltage V. Okay, so let's go ahead and proceed with these examples. In A, we have 4 resistors. The first step is to remove the source. Plus minus Vs, remove the source, and open up the terminals. A, B, and then we have 3 resistors, and all of them are in parallel. And this is R1. So once we remove the source, we have 2 open terminals. Those terminals are the measurement terminals. That is the place where we want to find the total REQ. Okay. So in the previous topic, we learned about reducing and finding REQ. So this is how we are going to apply that. We take the source out of the circuit. We have open terminals, and REQ is between A and B, measured between A and B. So we start at the farthest end, and we reduce it towards A and B. I can see R4 is in parallel with R3, which is in parallel with R2. And that combination would be in series with R1. Again, R2, R3, and R4 all share the same node. And once you reduce it to one single resistance, you have R1, and let's call this R5. You'd have R1 and R5. And you can see R1 and R5 are joined together at one node, so R1 and R5 are in series. Yes. Yes. So the question being asked is if R1 was between R2 and R3, either at the top or at the bottom, then R3 and R4 would be in parallel, and that parallel combination would be in series with R1, which is something we'll see here. Actually, no, not in this one. But yes, R3 and R4 would be in parallel, and that parallel combination would be in series with R1, and that would be in parallel with R2. Yeah. So let's find the answer for this. R5. Somebody actually calculate this for me, please. 1/20 plus 1/30 plus 1/40. What is the answer for this? Anyone? Give me 4 decimal places. $9.2308. What's the fifth? 23076. Okay, we'll stick with 8. Thanks. That's a 9.2308. So that's R5. So my total REQ is 10 point. Oh, sorry, not 10. 19.2308 ohms. Okay. Now, apply Ohm's law because we have one single resistance. My total current I. Oh, actually, not one step at the beginning, at the top. Vs 20 volts plus at the top, minus at the bottom. Which direction is the current flowing? It's going up because for a source, current always goes from low to high. It's supplying, so minus to plus. So current supplied by Vs is going up top. There's nowhere else to go except through R1, and you can see if I label this as I can see that I is the same as I1. That makes sense to everyone, right? Current has nowhere else to flow. So it's going through R1. So total current I is simply Vs divided by REQ. And again, someone give me the answer for this, please. 1.4 places. That's it. Okay. All right. 1.04. I have I1. I1 is equal to I. So it's 1.04. If I have the current flowing through a resistor, I can now apply Ohm's law and find the voltage drop across that resistor. So again, we had a large network of resistances. We reduced it down to one single resistance, applied Ohm's law, found the total current in the circuit. Now we expand the circuit back up again in the exact same reverse order. Okay, so the first step would be to find current I1. Current I1 is exactly the same as I, so I got 1.04 amps. If I have 1.04 amps, I have I and I have R, I can find voltage. Voltage VR1 would simply be I1 times R1. In this case, 10.4 volts. 10.4 volts. Straightforward? Makes sense to everybody? Any questions? Okay. So now our circuit is still this, R1, R5, right? So I don't have the source in here, but the same current I is flowing through R5. R5 is a combination of R2, R3, and R4 in parallel, right? So I is going through R5. If it's going through R5, I can calculate the voltage across R5. Same way as R1. Or what else can I use? Voltage, loop, VL, KVL. I can use KVL to find the voltage across R5, or I can apply Ohm's law. Two different analysis techniques, two different tools. You decide which tool you wish to use. Make sense? Again, all of these analysis techniques are tools in your toolbox. Unless a question specifically asks you to use a specific method or a technique, you're free to choose whichever technique you want. Now, if I'm asking you to solve a problem using series parallel analysis technique, the larger method is clear to everyone, right? Within that larger method, you can apply KVL, KCL, Ohm's law, whatever you wish. But you have to show the larger method to me, okay? All right, so I can find it using Ohm's law, or I can find it using KVL. So VR5 would simply be 20 minus 10.4, and I would get 9.6. You can also do 9.2308 times 1.04. Someone do that and give me the answer, please. Oh, not 10.4. 1.04. What's the answer to this one? Perfect. Now, this is the reason I asked for 4 decimal places. If it was only 1 or 2, then I would have what, 9.23 as my total equivalent resistance for R5, right? So if it was 9.23 right here, if I took only 2 places, 9.23, my answer would be, instead of 1.04, I would have 1.05. This is just to illustrate something to you as engineers, okay? 4 decimal places versus 2 is going to give you a slightly different answer. I won't deduct points for that. It's just that some problems, depending on the values of the components, you would end up with a slightly different answer. So if you take 9.23, your REQ would be different. Your REQ being different would give you a different value of I. And because of the different value of I, your voltage here would be different. It would not match up. This 9.6 would become something else. Okay. So we have the voltages. From that point on, you can easily find the current through the three resistors: IR2, IR3, and IR4. Or wait, in the circuit it's given as what? I2, I3, and I4. Simply apply Ohm's law, and you find the total current flowing through those three branches. All right, 10-second pause. Let me know if you have any questions. Yes. Mm-hmm. Yes, absolutely. Again, so the question being asked is, we found the voltage across R5. So is the voltage the same for all three resistors? And the answer is yes. So at any time, if you have a parallel combination of resistors or a parallel combination of components, the voltage that appears across those components is a result of all of those resistors working at the same time. And that's the reason why the voltage is the same. If you remove even one of those resistors from the circuit, now the combination has changed. The voltage that appears is now different, but it'll still be the same for all of those resistors in that circuit. Yes. Yes, because the voltage changes, so the current would change depending on the value. Does that make sense to everyone? Okay. All right, so let's see. B, we would solve the exact same way, but I can tell you right now, or I will let you tell me, what do you see here? You can solve this by logic. You have 2 amps going here, and then it splits. It splits in 2. If you look at the 2 branches, what do you see? 5 and 15 in series, you get 20 ohms. 10 plus 10 in series, you get 20 ohms. Both branches are equal. So this branch and this branch are exactly the same. So if you're splitting a current in 2 and both have the exact same value, what is it that we're doing? We're just splitting it in half, or 2 equal halves. So logically, 2 amps being split in 2, I should get 1 amp and 1 amp. That's just by logic. You don't even need to be an engineer to solve that. Yes. This way? Like this one? Or this one? So R3 would be here or here? No, then the circuit changes. So it depends on how it's configured. If R3 and R4 were in front of R1 and R2, it'd still be the same parallel. I could draw the circuit schematic. So the question being asked is, does the placement of the components matter? And the answer is no. I could have a current like this. I could draw the exact same circuit like this. And schematically, to our eyes, the circuit looks different because I'm drawing R3 and R4 on the left, but electrically speaking and mathematically speaking, they're exactly the same connection. So if this was R1, R2, R3, and R4, it'll still be the exact same circuit. Your current goes to a junction, it splits in 2, and then those resistors are in series, and it splits in the exact same manner as the value of the resistance. Does that answer your question? Okay. All right, so let's see how we can apply this technique. Again, that was just logic, just to make a point. But if you were to follow our methods, as I said, we would reduce the current source, we would take it out, and then, not there. And so this is 5, 15, 10, and 10. Req is simply R1 plus R2 in parallel with R3 plus R4. 20 in parallel with 10, sorry, 20 in parallel with 20. Simply be 400 divided by 40 for 10 ohms. Req is 10 ohms. And if Req is 10 ohms, I can find the total voltage that appears across that circuit. Now remember, current going through here has caused a voltage drop here, and a voltage drop here, and the voltage here. But that voltage will be the same, again, because it's a parallel network. So between those 2 points, up top and at the bottom, the voltage remains the same. So if I label this as V, my V is now equal to IS times Req. So IS is 2 amps times 10 gives me 20 volts. And 20 volts appears across the first branch as well as the second branch. So 20 divided by 20 gives me 1 amp. In the second branch also gives me the exact same thing. I1 is V divided by R1 plus R2. 20 divided by 20, 1 amp. And I2 is also 20 divided by 20, 1 amp. And once you have current, you can also find the voltage for each of those resistors. All right, 10-second pause. Let me know if you have any questions. Yes. Oh, that's the first branch. So Ohm's law. I1 is coming down. I'm applying Ohm's law where it's I1 being divided by the total resistors in that series network. So R1 plus R2. The same for the other branch also. Does that make sense to everyone? Any questions? Once I have voltage and current for every resistor in there, I can find power, right? Power for resistor R1, power for resistor R2. It simply be VR1 times I1. Can find energy. We haven't looked at energy equations yet, but you can, once you have voltage and current, you can find any other quantity in the circuit. Okay. On a side note, at the beginning I said quiz will always, test material from the previous week, preceding week. It will not specifically ask you for the material that you learned before in the prior weeks, but I mean, students should have a foundational knowledge of everything they did before. So for this week, we are learning about series parallel equivalent techniques. I will test on that on Monday. I will not specifically ask or test you on Ohm's law or KCL or KVL, but students should know how to do those. Does that make sense? I will not specifically ask you to show me how to do that, but in order to do these larger techniques, you need to know the foundational ones. Okay. No more questions. Then we will look at this example C. Example C, again, is straightforward. Let me draw it out here. Voltage source, I'm going to take it out. So R1, R2, R3, R4. This is 10, 15, 40, 25. 10, 15, 40, and 25 ohms. A and B, this is where I'm measuring REQ. My REQ is starting at the farthest end. I see R4, and R4 is in series with R3. Okay. It is connected to R3 by this node up top on the right, and one single node. There is no other connection at that node. Anytime you see a electrical junction or an electrical node with only two components, it's in series. As long as it's part of the circuit, they are in series. Okay, so here you see it's a junction, it's a node, and there's only two components connected, R3 and R4, and so they are in series. And they will be in series at their outer terminals. The outer terminals for R3 and R4 are right here. That's how you want to quickly identify components in series and parallel. All right, so R3 and R4 are in series, and then they're connected to R2 at their respective terminals. So that means that they're in parallel. And if they're in parallel, they now share a node with R1. So I can say that entire combination is in series with R1. Let's call it R5. And I will call this R6. So far, so good. What do you notice about the two branches? R4 plus R5, what does it give us? Value. Sorry, R4 and R3. What value does R4 and R3 give us? 40 ohms. That's why I like these examples. So it's 40 in parallel with 40 plus R1, which is 10. So 20 plus 10 go to 30 ohms. So my total REQ is 30 ohms. Voltage is 30. Was it 30? Let's see. Yes, voltage Vs is 30. And so the total current I flowing in the circuit, simply Vs divided by REQ. So it's 30 divided by 30. Gives me 1 amp. Actually, let me go back up here again. One thing I forgot again. Current for Vs going from minus to plus. So it goes in that direction. Again, I can see I1 and I are exactly the same. I'll make the same notation here. Total current I supplied by Vs is equal to 1 amp. Make sense to everyone? All right, questions? Now it's the same thing as problem number C. You have I1 entering a junction where it splits in two, right? Let's go back to this circuit, less messy. So I is the same as I1, right? And then it's that junction and it splits in two. and both branches have the same value, 40 and 40. Actually, it doesn't matter what that value is. It could be 100 and 100 or 1,000 and 1,000. As long as they have the same value, that current is splitting in exactly equal halves. And if the exact equal half, then you can simply write I2 would be equal to I3, I divided by 2. Actually, let me not do it this way. Let's just stick with the technique. This just works out because the examples are nice and have, nice round numbers that give us nice equal values. But let's do it the way we're supposed to. So is in the previous example, I is also flowing through R6. So I can write VR6. Again, R6 is the parallel combination of R2, R3, and R4, right? Similar to that example A. Would be I times R6 1 times, what was R6? 20. So 20 volts. VR6 appears across here, plus and minus. VR6 appears across these two nodes right here, top and bottom, plus and minus. Current is going down, so if current goes down, point of entry is plus, point of exit is minus. These nodes, when you measure the voltage, should give you 20 volts. Also from KVL, we know if 1 amp is going through a 10 ohm resistor, voltage drop across that resistor is 10 volts. 30 minus 10 gives me 20. That's a verification check. So again, you can use KVL or you apply Ohm's law going through R2 to determine VR6. Think over it. Let me know if you have any questions. That makes sense to everyone? You can apply KVL or you can apply Ohm's law. Your choice. And once you have VR6, you can find I2, you can find I3. VR6 divided by R2 gives you I2, and VR6 divided by R3 plus R4 gives you I3. In this case, it would be, 20 volts divided by 40, half an amp, which is what we obtain by just solving it logically. Make sense to everyone? Any questions? Any questions at all? Okay. There's a technique I want to show for reducing a large network of resistances into one signal resistance. And this technique pretty much applies to any circuit, any network. As long as the circuit is reducible, this technique will work. There will be circuits that we cannot reduce. Okay, there will be circuits that we cannot reduce. And for those, we use different analysis techniques. But for circuits that are reducible down to one single resistance, this technique will work. So I'm going to draw out, let's see, problem number B. B had what? R1 and R2 R3 and R4. R1, R2, R3, R4, right? That's the problem. And these are the measurement terminals where we want to find REQ. So this technique, what you do is you draw out two horizontal lines spaced far apart. these horizontal lines note they are noting the measurement terminals. Our objective in this technique is to draw every resistor vertical from A to B. Okay, that's our goal. We are going to divide it into equal branches. So first step is to draw out our measurement terminals, two horizontal lines spaced far apart. Again, this one only has like 4 resistors, but a larger network might have like, 10, 15, 20 resistors. So you want to give enough space to draw everything out. So A and B. We start at the top. What resistors or which resistors are connected to terminals A? Which ones? R1 and R2, right? If you look at connection at A, you have 2 resistors, R1 and R2. This is A right here. So I'm going to draw out R1. What else is connected at A? R2. So I'll take R2 and draw it out here. Again, give enough spacing because we don't know how the circuit's going to develop. So I'm done with A. I don't worry about A anymore. I go to the other end of R2. Where is the other end of R2 connected? Right here. And what do I have? I have 2 more resistors connected to R2, which is R3 and R4. So 2 connections. So like a flow chart, I'm going to draw out 2 more resistors, R3 and R4. Then I want to complete the loop. Where is R4 going? R4 is going to terminal number B. And that is the goal. We want to go from A to B, and that is how we are going to draw our resistors. So R4 goes to B. I'm going to drop a vertical line going straight to B. R3 is the same. It goes to B. And then finally, R1 also goes to B. All my resistors are nice and vertical. Now I can begin reducing. The goal here is I've divided my circuit into branches, and every branch is parallel. So I could have, this is one branch, this is a second one, I could have a third, I could have a fourth, I could have a fifth, as many as needed. But the point is, once you have all the resistors drawn out, every branch is between those 2 nodes, so all of them are in parallel. Then you simply reduce every single branch down to one single resistor. R1 is already single resistor, so we don't bother with that. We come to R2, R3, and R4. R2 is connected to R3 and R4. It's neither in series nor is it in parallel. So we cannot reduce that directly. However, R3 and R4 are in parallel. They're connected at the top and they're connected at the bottom. Same nodes. So they are in parallel. So REQ as measured between A and B, I get R4 in parallel with R3. And that would be in series with R2. And finally, that entire branch is in parallel with R1. Yes. You can draw it with or without the diagonal. But again, this technique, if you apply, you don't need to redraw this at all. We simply follow the pathway. We start at A. What is connected to A? R1. Then we draw out R1. Then we have R2. So we draw out R2. Then what else is connected at the other end of R2? Well, we have R3 and we have R4. So we draw out R3 and R4 at the other end of R2. So we don't have to redraw the diagonal either horizontally or vertically with this technique. You simply follow the pathway and you draw each one of them vertically. Yes. No, because they're connected at one end like this. However, the other end of R2 is going here. And so, no, they're not in series. If there was no connection here and you're simply measuring at that terminal, then they would be in series. I see your point. So the question being asked is why is R1 and R2 not in series? Well, the answer is because the other end of R2 is connected to R3 and R4. That's why it's not in series. However, R2 is in series with R3 and R4. So R3 and R4 are in parallel. We reduce that first, then it is in series with R2, and then that would be in parallel with R1. So it would not be in series that way. So in your homework, there will be one problem in homework. I can't remember which homework, but there's a diamond-shaped circuit, and there's a short between the top and the bottom terminals. You would be able to solve that problem with this technique. And a similar circuit will also appear in the series parallel homework. And so again, you would be able to solve that circuit using this technique. Okay, no matter what the schematic is, as long as it is reducible, you can use this technique. It'll work. There's also a lab that will come, I think lab number 3 or 4, where you have to find the equivalent resistance, and you can use this technique to do that. All right, any questions? Okay, let's move on then. Our next topic is voltage division. So we have voltage division and current division principles. Both of them kind of very similar to each other. When you have a series connection of components, and in this case, of course, we're talking about resistors. So we'll say when you have a series connection of resistors, the same current flows through that circuit. However, a voltage is dropped across each one of those resistances. So when a voltage is applied across a series connection of resistors, a fraction of that applied voltage appears across every resistor. And the fraction is given by the value of that resistor to Req. It's quite wordy, but the equation itself is very straightforward and very simple. So here we go. Derivation is not important as long as you understand how to apply that voltage division equation. So in this case, I have a voltage that is V total, current I. Current I also flows through the rest of the circuit. I can write my Req, because it is a series connection of resistors, it is simply R1 plus R2 plus R3. Right? R1 plus R2 plus R3. I is simply V total divided by Req. Ohm's law. And since that same current I flows through every single resistor, I can apply Ohm's law in reverse and find the voltage across every single resistor. So VR1 would be I times R1 and I in this case is VT. And so I can rearrange the terms and I can write R1 or Req. That's it. That's the derivation. And that's the voltage division equation. So I'll give it 5 seconds. Okay. So as I was saying, quite a wordy description. So let's break it down. When you apply a voltage to a series network of resistors, a fraction of that voltage appears across each one of those. So VT is now divided into V1, V2, and V3. Current is not divided. It's rather easy to see because it's a closed loop. So the same current I flows through every single resistor, every single component, right? Everyone sees that, right? The only thing that changes is the voltage that appears. So it's V1, V2, and V3. V1, V2, and V3 are a fraction of VT. And a fraction is given by the corresponding resistance to Req, or by the ratio of R1 to Req. So again, as I said, the description was quite wordy, but the equation is rather straightforward. VR1, the voltage appearing across R1, is a fraction of VT, and the fraction is given by the resistance, or the ratio of the resistance R1 to the total sum of the resistors Req. So it's simply applied voltage times R1 divided by R1 plus R2 plus R3. Does that make sense? So if you apply directly for VR2, I can write it's a fraction of VT. The fraction will be given by R2 over Req. Same thing for VR3. VT times R3 over Req. And that's it. That's the voltage division principle. You can have this in your equation sheet so that you can remember it. You don't need to derive it. You don't have to show me that you derive it, as long as you understand this and know how to apply this equation. Okay. So if I ask you in a quiz, solve this using voltage division principle, you should be able to apply it directly. Yes. Yes. So question being asked is, where is the voltage coming from? That's a good question. If this was a supply, power supply supplying, if this was a source, if V total was a source, V1, V2, V3, obviously current is flowing through there. But let's go back one slide and look at this, specifically B and C, sorry, A and C. Remember, when we solved problem A, we found the voltage across R1, and then we found the voltage across R5. Make sense? And then we say voltage across R5 is exactly the same because they're in parallel. Now, if we do that for a series connection of resistors, as in C, we found the voltage across these 2 points, right? These 2 points right there. So if you take and isolate that portion, what do we see? That voltage is applied across R2 and is applied across the series combination of R3 and R4. So instead of applying Ohm's law to find VR of 3 and VR 4, I could simply apply voltage division and find it that way. So that's a third technique. So let's see, where was C? C is right here. Okay, we found VR6 was 20 volts. That same VR6, let me redraw the circuit in a way that makes sense. So this was R1, R2, R3, R4. It's the exact same circuit, okay? I have not changed the circuit. I've just changed the schematic. That's it. Does everyone see that? Okay. So plus minus, that is VR6 applied across a series combination of R3 and R4. I can find the voltage across R3 and R4 directly. And VR3 in this case would simply be VR6 times R3 divided by REQ in this case would be R3 plus R4. And you can solve it using Ohm's law, and you will see that you arrive at the exact same answer. Does everyone see that? Does it make sense? Okay. I was going to do an example, but we are out of time. So we'll pick up here again on Monday. Again, I will hold class as usual. While I understand why the strike is going to happen, the people who end up suffering will be the students. So I don't want to see that. Anyway, Monday quiz, and then I'll post an announcement on Canvas. Last time I sent an email. Typically, I post an announcement, so it's all in one place. So again, quiz 2 announcement will be coming later today once I finish class and office hours. So look for that announcement. And again, have a good weekend, and I will see you on Monday. If you have made plans to go home for the week, you can absolutely do so. You can attend online.